Eric Burgess here, a guidance counselor, randomly surveyed female students ages 16 through 18 years and asked if they work. The data is shown here. So here's our data, and they want us to find some probabilities. So first up, part A, complete the table. So all that's missing from this table is here we've got the age of the girls, and here we have the number that work and the number that don't work for the age group, but we're missing the totals that go here and here. So we're simply going to calculate those. So first up, we just add down to get that total. So that's just 87 plus 157. And we get 244. So we put that in 244. Next, we do, for 17 years old, we have a 62 and we've got a 42. And we get 104. And then we do the next one. That's going to be 42 plus 79. That gives us the total going downward at 121. Let me change to black here. All right, so now we want the totals going across. So this is going to be the total number that work, right? Before this was all the 16-year-olds, all the 17-year-olds, and all the 18-year-olds. Now we're going to go across, find all the people that work and don't work. So that's going to be 87 plus 62 plus 42, and we get 191 there. And we're going to go across the don't work, and that's 157 plus 42 plus 79. And we get 278. All right, so we could check our work here actually by getting the total here. So we have to complete the chart, but we can get it adding across or we can get it adding down, and they should be the same number. If they're not, then we messed up. So adding down, we get 191 plus 278, and we get 469. Now let's check that really quick. We'll do 244 plus 104 plus 121, and we get 469. So we are very confident this is correct, and that's important because all the later answers are going to rely on this. Okay, so let's do part B. So part B asks us to find the probability of work. And so just looking at this, we say, well, the probability of work, well, let's think. A probability is always the sample space over a condition. In this case, the condition is work. So the condition is work, and the sample space is everyone. Everyone. So we have everyone, they're right here in total, 469. So we put 469 on the bottom. And then the top is everyone that works. And so we say, okay, well, here's all the work category, and everyone that works is 191. So we put 191 on top. That's going to be equal to, now you could leave it as this, or we could try and reduce it. So we're going to do 191 divided by 469. And we get 0.407, or you could also write 40.7%. All of these are forms of the answer, and then we would box this. You'd say, here you go. You could box the fraction as well. It's also a form of the answer. All right, now we're going to go to part C. So they want for part C, let me scroll over here, that they don't work and that they're 18 years old. Okay, so we've got a new condition. We've got this and condition. So and means it needs to fulfill both conditions at once. And so if we look up here, we've got the not work category and 18-year-old category. So we go to not work and to 18. So here's all the people. Let me do it like this. Here's all the people that don't work in this row. Here's all the people that are 18. The only one that's circled twice is this 79. So 79 is our top number because it does both our condition, which is they don't work and they're 18 years old. So that's 79 over. So what's our sample space? Well, here again, we were considering out of everyone, what are the people that don't work and are 18? So we were looking at everyone. So again, it's this total up here, 469. So we put 469 on the bottom. And we can convert that as well. So we put 79 divided by 469. And we get 0.168 or 16.8%. Whatever floats your boat. And you could like just box all this stuff. And if you want to be really fancy, you could even write the conditions in word form. All right, so let's go to part D. So part D has that they work or they're 17 years old. Now this one's a bit different. This one says or. So or, it could be, we could get people that work or 17 years old. Like it could be either or. They don't have to fulfill both at once. They could do both or they could do just one. And so in this case, we look, okay, well, let's see here. Let's do our circling method again. I'm going to use a highlighter this time. So the people that work are the people up here. The people that are 17 are the people right here. Whoops, that's 18. 17 are right here. So we want to do each one of these numbers only once. So notice that the 62 falls in both categories. We only want to count it one time because we don't want to make it look like there's twice as many as those people. There aren't. There's only 62 of them. So what we're going to do is we're going to say, okay, well, the bottom, what's our sample space? Well, our sample space is still everyone. We were looking at the entire chart to determine this. And so we still say it's everyone. So the bottom number is 469 people. And then the top is just all these things that we've highlighted. So we just add them all, and you only add them once. You don't add the 62 twice because these are not mutually exclusive. So if you remember the mutually exclusive for the probability of or, so if we add a probability of A or B, the not mutually exclusive case is the probability of A plus the probability of B minus the probability of A and B. And so I know some instructors are big on you using the formal definition. And so you would write that out, and then you would write out each individual one. Here, we can literally just write these all out added together. So we could put 87 plus 62 plus 42 plus 42. There's two 42s. There's one here and one here. Plus 104. 104. And when you add all this up, that's the probability. Alternatively, you could write 469 using the formal definition. You could write 87 plus 62 plus 42. This is the probability that they work. These are all the work numbers, this row here. And then plus the probability that they don't work, so that's 469. Or I mean that they're 17 years old. So all the 17-year-olds are here. So that's going to be 62 plus 42. I accidentally counted the 104. The 104 is part of the totals. So we actually do not include it here. That could have been a big mistake. So that's plus 42. And so that's the probability that they are 17. So this is probability of work, probability of 17. And now we need to subtract off the probability that they work and are 17. And so the only one that did that was this 62 here. So we would do minus 62 over 469. And this would give you this is saying the exact same thing that this is saying. It's just a little easier to write. So we have 87, 62, 42, and 42. Don't write the 104. I accidentally highlighted part of the total. So, okay, we're going to type this in. So on the calculator, you can actually type fractions. I'm going to do it old school, though, and just use parentheses. So we use parentheses for the top. So we're going to put parentheses, 87 plus 62 plus 42 plus 42. We're going to close parentheses and then divide by 469. Now, because of PEMDAS, it'll do what's in the parentheses first. So it'll add everything and then divide. And we get 0.49, and I'm going to round to 7. So the 8 will round the 6 to a 7, or 49.7%. Now I'm writing equals here. It really should be approximately, but just understand that if you have a teacher that really wants it very precise, they may want to see approximate instead of equals because we're rounding. Okay, now we're going to go to E. Now E is got a symbol that I know throws a lot of people off. It's got this vertical line. So the vertical line means given that. meaning that we are making an assumption that they already fulfill the condition after this line. So we're assuming that the people already work. And what this does is it actually shrinks the number of people that we're looking at. I'm going to erase these. I want to erase the green. There we go. There we go. Okay, cool. So because it's 17-year-old given that they work, what that means is we only consider the people that work. Okay? So our new total, like before we were looking at everyone in all our previous probabilities, but in this probability, we only care about the people that work. We're assuming they're already a worker, like we already know this. So that means that our new sample space is all the people that work, which is 191. So the bottom number for our sample space is 191. And then our top number is that they're 17-year-old, but we're also assuming that they work. So that it's really 17-year-old and works, okay? So that's really there. So we're only considering the stuff we highlighted in green. So the 17-year-olds that work are right there. There's 62 of them. And I highly recommend highlighting or circling the given that, and those are the only numbers that you should care about for these kinds of problems. It can help you sort of visually see it. So here, the 17-year-olds that work, that's 62. So we put 62 on top. That's all you got to do. I know this line looks scary, but the general formula for it is just highlight everything that fulfills that condition. So in this case, we highlighted all the work. And then we said, okay, well, the sample space is all of this. So that total was 191. And then the 17-year-olds that were highlighted are right here, is 62. That's like saying 17-year-olds that work. Okay, and then I'll leave it up to you to go ahead and simplify the fraction. You've seen me do it several times now. And now we're going to move over to F. All right, so F's got a concept question. Are the events work and 17-year-old independent? How do you know? So there is a rule, actually, kind of similar to our OR rule, that can tell us if two events are independent. So we say the probability of an event, let's call our first event A, given probability that B has happened, is equal to A, probability of A, meaning that A is the same probability regardless of if B happens or not. So consider like flipping a coin. If you flip a heads, does that change the fact that you might get a heads or a tails on the next flip? Does the next flip, our next flip, depend on what we got on the previous flip? And we would say, no, you could have flipped 3 heads. The chance of you getting another heads is still 50-50. It's not influenced by previous coin flips. So this is called our independence rule, and we're going to use this to check what it's asking us for. So it says, are the events work and 17-year-old independent? So we say, okay, well, we could check this. We can check that, well, work, the probability of work given that they're 17-year-old. So we could say it like this. Probability of work given 17-year-old, is that equal to the probability of work? If it is, then we say the probability of work and them being 17 are independent. And so let's just really quick compute these probabilities. So for 17, sorry, the zooming in and out, but the screen the screen I'm looking at and writing at is actually zoomed in differently than the one that's on the screen you're seeing. It's kind of confusing. So we want probability of work given 17. So we say it's given 17. So we highlight all as 17. So the total for 17 is this 104 that's right here. So we write that in as our bottom number, 104. And our top number is all the people that work in there. So we say, okay, well, the only workers here are the 62. So we put 62 on top. Is that equal to this next probability? And that's the probability of work, just work in general. Well, we found the probability of work earlier in part B. So we go to part B and we got 191 over 469. And when we converted to a decimal, we got 0.407. Is that equal to this over here? Well, let's find out. We're going to turn it on and we're going to type a 62 divided by 104. And it's probably not based on this. Yep, we're at 60%. So we've got 0.59. We're going to round to 3. And we say this is not equal. And that's how we would know. So this is how we know. We know. And so we would say therefore not independent. And the not independent is because there appears to be some influence of the fact that they're 17 and if they work. And in real life, this makes a lot of sense, right? Because as you get older, your chances of getting a job go up. So the chance that you work would be influenced by your age. So that's how you do these types of questions. They're all pretty much kind of the same flavor. Once you have a grasp on and or and given that, you pretty much have a grip on all of it. And then just make sure that you understand this independence rule. If you've got the independence rule memorized, and it's not very hard, you just write given that, and then just say, what if does B really matter? If it doesn't, then the probability of A shouldn't be changed by B. So they should be equal. And that's that. If you have any questions, let me know. If you're a Citrus College student, stop by online tutoring, and we'll catch you in the next problem.